Hello everyone, hopefully you're doing well. In this video, we're going to start with chapter 5, probability distributions. In this one, what we're gonna do, we're gonna learn how to create tables of what we expect to happen in terms of probability, create a table describing what we expect to happen instead of what did happen, because in the previous video, we focused on probability, like using real sample data to find actual results, or we find probabilities for each possible outcome. But for this one, what's going to happen? We're going to find the probability, then find the population mean, mu, and population standard deviation, sigma. For it on the first sections, let's focus first of all on how to find probability distributions. We're going to define random variable and probability distribution. We're going to determine whether the requirements of a probability distribution are satisfied when given values of a random variables along with their corresponding probabilities. We're going to compute the probability and standard deviation of a probability distribution. So we're going to talk about what's the probability distribution means exactly. The mean and standard deviation can then be used to determine whether results are significantly low or significantly high, or neither. As a key concept for each chapter, we said that for this section, we would introduce the concept of a random variable and the concept of probability distribution. We illustrate how a probability histogram is a graph that visually depicts the probability distributions. Like we construct probability, we construct histogram before for quantitative data, but here we're going to show how to find the important parameters of mean, standard deviation, variance for a probability distribution. Most importantly, we describe how to determine whether outcomes are significantly low or significantly high, or neither, things that we already covered in the previous chapters also. As I said, if for some reasons you miss what we just did in the previous chapters, I strongly advise you to go back and watch those videos. So without further ado, let's talk about some basics. We're going to begin with the related concepts of random variable and probability distributions. We said that random variable, because we can talk about it. Random variable is a variable typically represented by x. Like random variables, if you do random variable x, that might be 0, 1, 2, 3, 4, 5, etc. Those are random variable that has a single numerical value determined by chance for each outcome of a procedure. So random variable, you flip a coin, you obtain a head. So those are, no, sorry, you toss a die, you obtain a 4. You toss a die, you obtain a 3. So those are random outcomes. So but for probability distributions is the description that gives the probability for each value of the random variable. If you toss a die, there are 6 possible outcomes. You either obtain 1, 2, 3, 4, 5, or 6, because we have 6-sided dice. So probability of obtaining 4 is 1 out of 6. But probability of obtaining an even number, because from 1 to 6 you have 3 even numbers, 2, 4, 6 is 3 out of 6, right? So we call that probability distribution. It is expressed in the format of tables, formula, or graph. So for the probability distributions, we're gonna do it for each of them separately, so then we can continue. Now, another key concept, we made a distinction between discrete and continuous data. So random variable may also be discrete or continuous. So that's what we're gonna do here, because for us, a discrete random variable has a collection of values that is finite or countable. So for example, let's say number of phone calls in a day for a salesperson. So number, we said number of phone calls in a day for a salesperson. let's say a salesperson will make phone calls, to sell anything. So remember, the number of phone calls can be one phone calls, two, three, four, five, six, seven, eight, nine, 10, etc. So you see those are whole numbers, and so or number of M&Ms, yellow M&Ms in a bag of M&Ms, number of yellow M&Ms, in a bag. So those are discrete random variable. They have a finite. All right, they have a finite number. So if there are indefinitely many values, the number of values is countable if it is to count them individually, such as the number of tosses of a coin before getting heads, we can do that. But also, we can talk about continuous random variable. So what we mean, we said anytime we have your data that are varied, also variables, you can have either it's discrete, okay? Data can be discrete or continuous. All right, so a continuous random variable has indefinitely many values, and the collection of values is not countable. So that is important to count the individual items because at least some of them are on a continuous scale, such as a body temperature, or you said in amount of minutes, no, number of hours spent in phone calls by a salesperson. You see, when number of phone calls, number of calls in a day for by a salesperson, which number of phone calls can be 1, 2, 3, 4, 5, 6, etc. Number of hours you can spend, 2.5 hours, 2.75 hours. 5.3 hours, so because at some point there is a possibility of not getting a whole number, so we can say, and it can be indefinitely in terms of fractions. So you said it's continuous. So talking about because this chapter deals exclusively with discrete random variable, but I think in the next chapter probably we're gonna talk about the continuous random variable. So probability distribution when we deal with random, for discrete variables, every probability distribution must satisfy each of the following three requirements. You need to put these down. Anytime they ask you, is this distribution a probability distribution? You need to verify these three requirements. First of all, there is a numerical, not categorical, random variable x. So we don't construct a probability distribution for qualitative data or categorical data. We construct it for quantitative data, numerical. X is equal to 0, 1, 2, 3, 4, 5, 6, etc., but not like words, okay? Its numbers values are associated with corresponding probabilities. Second of all, in order to consider a distribution, a probability distribution, make sure you always verify the total of all probabilities. When you add them up all together, it's equal to 1. It doesn't exceed 1. All right, so it must be equal exactly 1. But at some point, if you find it 0.99999, or if you find 1.001, it's also acceptable because we have rounding errors. But expect, like, when you add up all your probabilities, it must be equal to 1. And the third requirement, no negative probabilities, no probabilities above 1. So you must verify these three conditions in order to state the distribution is a probability distribution. First of all, you verify that those are all quantitative data, not qualitative data, not categoricals, right? The X values are 0, 1, 2, 3, 4, 5. And second of all, always add up all the probabilities to make sure the total is 1. And you verify in your table there is no probability less than 0, or there is no probability greater than 1. So when you add them up all together, it's must be equal to 1. So no negative probabilities, no probabilities above 1. All right, no, above 100%. So make sure it can also be equal to 1 exactly, or maybe 0 exactly, but nothing below 0 and nothing above 1. Let's go very quick with this example. So what they ask you to do in this one, they're gonna ask you in this first example, the accompanying table lists probabilities for the corresponding number of unlicensed software package when 4 software package are randomly selected. In that tables, first of all, we need to verify. They said, what is the random variable? First of all, we need to make sure we're dealing with numerical data, like the quantitative data. The first column, there is no words, they are all numbers. Yes, x's are 0, 1, 2, 3, 4. So we are certain it is okay. The first questions we can answer. So the random variable x, they said, what is the random variable x? The random variable x is the number of unlicensed software package, right? So the random variable in x, right? This is x, that's a random variable, x, right? And the possible outcome for this, we know it's x equal, can be 0, 1, 2, 3, and 4. Are these values numerical? Do you feel like those 0, 1, 2, 3, 4 are numerical? Yes, the values of the random variable x are numerical. Yes. Yes, they are numerical. Now, is the random variable given in the discrete continuous or discrete? You need to verify that too. Yeah, actually, remember, continuous is uncountable. We don't have the whole numbers like this, 0, 1, 2, 3. So that must be discrete. And of course, as a hat, I told you that in this chapter, we're going to deal with only, discrete probability. So that would be discrete, right? It is discrete, right? So the random variable is discrete if it has a finite number of values or a countable number of values. Here, the random variable is discrete because it has 5 possible values, and 5 is a finite number. So you see, you have 1, is like 1, 2, 3, 4, and 5 possible values. So, and that's finite. So we're gonna stop there. Is the sum of the values equal to 1? All you need to do, add everything here together. You add this one plus this one plus this one plus this one plus this one. When you add everything together in this one, when you do 0.08, no, 0.08 plus 0.076 plus 0.265 plus 0.412 plus 0.24, answer is equal to 1.001. So we know that 0.01. Of course, remember in the previous one, we said that here, number 2, some x, assume all possible values must be equal to 1. The sum of all probabilities must be 1, but some such as 0.999 or 1.001 are acceptable because they result from rounding error. So we're gonna set the sum, because this one, when you add, the sum is not exactly 1 because of a rounding of error. The sum is close enough to 1 to satisfy the requirement. So also, the variable x is a numerical variable, a random variable, and its values are associated with probabilities, and each of the probabilities is between 0 and 1. We don't have any negative probabilities. Any probabilities be above 1. So you see it's 0.08, 0.076. They are all between 0 and 1, okay? Inclusive as required. The table described a probability distribution. Yes, a probability. Okay, so I'm gonna do that. That's the first examples. So I'm hoping you enjoy the first one. Of course, we're gonna continue to do more exercises in this case like that. So feel free to enjoy and have fun because we're gonna do it. Let's go with the second exercise because here our goal is to state whether or not. Okay, our goal is to state whether or not we have you know, um, we have probability, we have random variable that are discrete or continuous because that's what we're planning on doing. We need to check that, okay? Make sure you verify this with me very quick, okay? Yes, all right. Now, let's see it very quick, what we can do in this case. We need to see very quick what you can do in this one. They said, for the questions below, refer to the given values and then identify which of the following is most appropriate. Discrete random variable, um, continuous random variable, or not a random variable. We need to decide which one we're gonna do. All right, so very important. You know, we can verify that if you're okay with all of this. Okay, let's do it very quick. Okay, let's do it very quick. We said, you know, IQ, IQ score of statistics. So let's say if IQ, you know, statistic is IQ score of statistic students. Is it discrete, continuous, or not random variable? What type of numbers, you know? Let's do it. All right, so we're gonna check it because IQs are usually 120, 99, you know, so you can expect this one to be definitely discrete random variable. And exact height of statistics students, you know, the height can be 8.5, 8 point, 6 point something, 6 feet and 11 inches, 5 feet and 12 inch and 9 inches. Sorry, so we can have so many different ones, and also with a lot of indefinite fractions. So we can consider these numbers to be continuous random variable. This one is continuous. Shoe size of statistics student. Even though in shoe size, I put this one in parentheses for you to see. You can have a shoe size to be 8 or 8.5, but at some point it's a definite number because discrete variable take on specific separate values. You can have values in between unless explicitly allowed. So shoe size are usually recorded in specific steps, like size 8, 8.5, 9 in the US. And there is no such thing as shoe size 8.25 in the system. Because we don't have that in the systems, so we would consider this one to be discrete also. So this one is discrete random variable. Measure of statistics. Remember, for measure, what type of measures can we have? Remember the measures? All right. Oh, okay. Let me say before that, for C, shoe size is discrete, but if you take your foot length, what is your foot length can be a lot of decimals, right? Can be foot length can be you know I don't know, like 9.3 inches or 8 2 inches or 8.65 inches, so it all depends. For the shoe size, it's different from the foot length, okay? Let's go with D. Majors of statistics students, that not random variable for this one, not random variable. Why? Because remember, random variable for us would be like numbers, but here those are categorical numbers. Majors can be engineering, statistics, and biology, law, medicals, so those are not numbers, those are words. The number of rolls of a die required for a statistics student to get the number 4. Well, to get the number 4, is discrete because you know what you want. Number of students in a statistics number of students in a statistics class. Again, here, for this one, that would be again discrete because it's a finite number. Grades, ABC, because they said those are grades. ABC, not a random variable because those are letters, not a random variable. I'm hoping you can read my handwriting. Number of times a statistics student must draw a card from a shuffle deck before getting an S. Here, look at this one. It's number of times. I mean, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's definitely discrete. You have a discrete. Social security number. That's an attribute. All right. If you say social security number, it's an attribute. It's not a label. It's like a label. So that's not a random variable. I say RV. Exact on round age of statistics students. Again, those are continuous. All right. Now, the other ones we need to talk about, because as I said, we're gonna go a little bit faster on these, is to graph, a histogram to display, probability distributions. A probability histogram, remember, is similar to a relative frequency histogram, but the vertical scales now shows probabilities instead of relative frequencies based on the actual sample results. So probability histogram for numbers of females in 2 births, for example, that's something you can see in the book. Even there is a formula for the specific examples from the book. I strongly advise you to take a look. You would see also from the book that formula works in this particular case. I even go over any examples for you. The table lists countries along with the probability on licensed software in each country based on data from Business Software Alliance. There's a table describe a probability distribution. Do you think it's a probability distribution? No, look at the first column. Those are not random variable X. Those are countries. Those are words. So it's categorical. And also look at the total. No, it's violate 2 of our conditions, all of our conditions. The table violates the first requirement because X is not a numerical random variable. The values of X are categorical numbers, categorical data, not numbers. And the tables also violate the second requirement because the sum of the probabilities is 2.09, and we know the total of all probabilities must be equal to 1, even though all the probabilities are between 0 and 1. But when you add them up all together, it's add up to 2.09 instead of exactly 1. Because the 3 requirements are not all satisfied, we conclude that the table does not describe a probability distribution. In the test, of course, you're going to have questions like this. I verify whether this distribution is a probability distribution. Or first of all, verify that all probabilities is between 0 and 1. The first column are all X values 0, 1, 2, 3, 4, 5, etc. And when you add up all together, it gives you 1. Okay? Remember, that's something I want you to verify and make sure you see it's happen, because remember that with a probability distribution, we have a description of a population instead of a sample. Okay, so the values of the mean and standard deviation variance are from parameters. Remember here for us, a mean, we're gonna use the Greek letter mu. And for the variance, we're gonna use the Greek letter sigma square. So, and for the standard deviation, which is the square root of the variance, something we covered already, we're gonna only use sigma, right? So now the mean variance and standard deviation of a discrete probability distribution can found using these formulas. Those are the formulas we're gonna use. Take each x, random variable x, multiply with the probability to find the mean, and then you add them up all together. We have two formulas to find the variance, and because usually I prefer to use the first one, but if you use the second one, it's fine also. But the second one, it's better if you do it manually, but you can do it with your calculator. And remember, the standard deviation is the square roots of the variance. Remember, you just find the variance and you take the square roots of it. That would be the standard deviation. Let's see a few other examples very quick. Read these problems, because what we're gonna do here is read these problems and verify that whether the probability distribution, whether a probability distribution is given. So that means verify the three conditions met. If a probability distribution is given, find its mean and standard deviation. If a probability distribution is not given, identify the requirements that are not satisfied. So first of all, do you believe this is a probability distribution? No, it's not a probability distribution. This one cannot be a probability, not a probability distribution. Do you know why? It's not a probability distribution because the causes are not values of numerical. Look at that. Not numerical. Not numerical. Not, it's categorical data. Not numerical. Not a probability distribution. Let's see about this one. Oh, yes, the first column is numerical because you have 0, 1, 2, 3. So first condition met. Let's see for the second conditions, or we can try the third one first. All probabilities are between 0 and 1. Met. That's good. Now let's add them up all together. Okay. So the problems, if you add 0.0, look, if you do 0.12 plus 0.079 plus 0.213 plus 0.311. So the problem, the total is 0.617. So total 0.617. While the first two conditions met, but this one, total is not equal to 1, right? Not a probability right? Because sum of px is not equal to 1. So it must be equal to 1, If it's not equal to 1, then it's not a probability distribution. Verify all three. Now let's go with the next one. Because they said, if it's a probability distribution, we need to find the mean and the standard deviation. Now, let's try to go with the next one, because we definitely need to verify this. First of all, for this distributions, the first condition met because there's a random variable x, 0, 1, 2, 3. Now, all the probabilities are between 0 and 1. There is no probability less than 0 or greater than 1. Now, let's see the totals. Can you add all of them? If you add everything here, the totals is 1 exactly. So all conditions met, yes. It's a probability distribution. Okay, it's a probability distribution. Now, if it's a probability distribution, you must find the mean. Remember, for us, the mean mu is sum of x times p of x. So that means what we need to do here is to take x, every x you multiply with p of x. So that means you take 0 times 0.104, 1 times 0.351, you do 2 times 0.396, and here you do 3 times 0.149. So this is for us. You see, I extend the table. Yeah, I need to extend the table. Now, the total for me here, when you add everything you find here after you use your calculator, I believe the totals here would be 1.6. So for us, the mean is 1.6. Now, the next question is to find the standard deviation. Remember, standard deviation is sigma, because we're dealing with population, is the square roots. Remember, for the formula for this one, we went over it already. We said for the square roots of x minus the mean, raise it to power 2. No, we're going to say sum. We need to add them all together. So hold on. So we're going to have sum of x minus the mean, raise it to power 2 times p of x. So what we're going to do in this column right here is to make sure we add a column where we do x minus the mean, raise it to power 2, multiply it by p of x. So what's the formula? We said the x is 0 minus the mean, which is 1.6, raise it to power 2, multiply it by the probability, which is 0.104. Do the same for the second one. X is 1 minus the mean, 1.6, raise it to power 2 times the probability, 0.351. X is 2 minus 1.6 squared times the probability, 0.396. X minus the mean, population mean, of course, times 0.149. So now what the answer for when you take x minus the mean, power 2 times p of x, you need to find this one. And according to my study here, the total is approximately 0.81. So for us, sigma here would be square roots of 0.81, which is 0.9. Okay, that would be the standard deviation. So what we find here in the total is the variance, but because we're not interested to the variance, we take the square root of it to find the standard deviation. So that was a good example. Let's see what this one tells us. First of all, again, verify this distribution is a probability distribution. The first condition met because we're dealing with random variable x, 0, 1, 2, 3, 4, 5. The second of all probabilities are between 0 and 1. Now, check the total. What the total would be when you add all the probabilities. When you add all the probabilities here, exactly, it's going to be 1. So, yes, we can, it's a probability. This one, yes. It's a probability distribution. Okay, it's a probability distribution because all conditions met. It's a random variable. It's the total probability is equal to 1, and no probability is less than 0 or greater than 1. Yes. Now, the second question, so we know what we're looking for. We need to multiply every x with the probability. So that means you take 0 times 0.031, 1 times 0.156. Okay, we do 2, because it's x times p of x. 2 times 0.313, 3 times 0.313 twice, 4 times 0.156, and 5 times 0.031. So when we put the total together for this, total of x times p of x equal, sorry about this, 2.5. So for us, the mean mu is sum of x times p of x. That gives you 2.5. Now we know for the standard deviation, answer must be square roots of x minus the mean power 2 times p of x, right? So first of all, we need to make sure we put a table out there for this in the table, a column for that. So we're gonna do x minus the mean square times p of x. So meaning x is 0 minus 2.5 power 2 times 0.031, 1 minus 2.5 square times 0.156, 2 minus 2.5 square times 0.313, 3 minus 2.5, you see, I always subtract the mean from the random variable x. So the mean never change, times the probability for that column is 0.313. And we have 4 minus 2.5 square times 0.156. And we have 5 minus 2.5 square times 0.31. Okay. Now, this is something we just did, but as I said, we can do even better. When you add up all of this together, okay, when you add up, when you add up all of this together, that means we're gonna do sum of x minus the mean squared times p of x. We feel like the answer would be only 1.21. Now, knowing the standard deviation, sigma is the square root of x minus the mean squared times p of x. That means sigma is square root of 1.21. What is the square root of 1.21? It is 1.1. Okay. We answer the questions. And so far, I believe you can verify everyone if a distribution is a probability distribution before we move forward. But now, let's see. We covered this part already when we talk about significantly identify significant results with the range term of rule of thumb. You know, range one rule of thumb for identifying significant results. We said if it's significantly low, if it's below 2 standard deviation, and significantly high if it's above 2 standard deviation. But if it's between, the value is not significant. That means it's neither. But we also said significantly high of success, X success among N trial is significantly high numbers of success if the probability of X or more success is 5% or less. That is, X is a significantly high number of success. Is the probability of X or more is less than 5%. The value 0.05 is not absolutely whichever. Other values such as 0.01 could be used to distinguish between these results. So make sure that's something we can verify as well. Significantly low, also we said X values, X success among N trial is significantly low if the probability of X or fewer, remember, X or more is about significantly high, X or fewer is less than 5%, is significantly low. Okay, so verify that because we're going to use it. If under a given consumption, the probability of a particular outcome is very small, and the outcome occurs significantly less or significantly greater than what we expect with that assumption, we conclude that the assumption is probably not correct. Let's see for these examples, very quick, what they ask you to do for this one. They said, refer to the to this table which describe probabilities for the California daily fall lottery. The player selects 4 digits with repetition allowed, and the random variable X is the number of digits that match those in the same order that they are drawn. All right, find the mean and standard deviation. So that's the first thing we should be doing for this one. We need to find the mean and standard deviation. First of all, we need to verify if it's a probability distribution. I am certain it's a probability distribution because this is X. All right, X values is here. If we have our X values here, then we have the probabilities, total of all probabilities. You know what? Let me move it because we need more space for that. How about I do this one smaller? Because we need more space, okay? Let's do this one 16 because 16. And I can bring it all the way up to make sure we have enough space. And I'm going to erase those X here. Okay, I definitely think we have enough space because for this one, we know it's X values here, and total of all probabilities, when you do this total here, it must be equal to 1. So definitely equal to 1. Now you know to find the mean. Remember what the mean is? Mean is sum of X, P of X. So that means take X, multiply it by P of X. So you're gonna take 0 times 0.656, 1 times 0.292, 2 times 0.049, 3 times 0.004, and 4 times 0, okay? So when you do that, because our goal here is to make sure that the total of all probabilities, total of X times P of X is equal to a number. And so far the number would be 2.1. So the mean here is 2.1. That's the first question. The second question is to find the standard deviation. Remember, for the standard deviation, we need to take x minus the mean squared times p of x. Again, with your calculator, you can even go faster. You take 0 minus the mean, which is 2.1, raise it to power 2, multiply it by 0.656. 1 minus 2.1 times 0.292, 2 minus 2.1 square, of course, times the probability, 0.049, and 3 minus 2.1 square times 0.004, and 4 minus 2.1 square times 0. So when you add all of this, x minus the mean squared times p of x, I believe the answer again here is 1.21. So for us, standard deviation, sigma is the square root of x minus mu squared times p of x, square root of 1.21. So sigma is 1.1. Feel free to verify these because we're going to need them for the future reference. Well, now they said using the rule of thumbs to determine whether zero matches is they said we need to check that. Check if zero matches, is a significantly low number of matches. So we can verify this that way. Okay. We can do it to check if it's significantly high or significantly low. So look, zero matches, right? Zero matches is significantly, use the rule of thumb to determine whether zero matches is significantly low. I mean, what is the standard deviation again? Standard deviation is 1.1 and the mean is 2.1. All right. So significantly high numbers of drivers who say that the text, okay, who say that the text while driving is greater than or equal to, if you do, because they said significantly verify that the rule of thumb is significantly, do I say significantly low or significantly high? I believe we use the rule of thumb to 0. I need to verify this one, okay? No, that's something different. I believe I use a different ones. Why would I do that? No. I apologize. I think I messed up this because no. The mean is different. It's totally different. I use different numbers for this one. So I believe the totals here. Okay, let me correct this very quick. Check your calculator because I believe I messed up with my next one. Because when you add all these, it doesn't give you 2.1. If you do this, the total is 0.04. 0.4. So that would be the mean. Check the calculator. Everything is correct except that it's 0.4 for the mean. And the standard deviation, I apologize for that because I definitely made a huge mistake on this one. I just see it. So for us, everything is correct except the mean. I need to remove all the means because that's definitely the next exercise, but still the same thing. So minus 0.4, 0.4, that's the mean, 0.4, 0.4, 0.4, okay? So meaning the totals, when you add up everything, you know, if you add up, let me check, grab my calculator. If you add up everything, it's 0.36. Now, remember the mean, that's the variance, but you need to take the square root of this. If you take the square root of 0.36, answer, in this case, what the standard deviation would be, the standard deviation would be 0.6. Okay, apologize for this mistake in finding the mean and the standard deviation. I didn't look at my notes, I just did it, knowing that would be the answer, but that's not the case. All right, now let's see for the next one. We said use the rule of thumbs to determine whether zero matches is significantly low numbers of matches. What we can say here is that significantly low numbers of matches are less than or equal to standard deviation. Let's see, mu minus 2 standard deviation. What you're gonna find, let's see, if you do 0.4 minus 2 times 0.6, what the answer would be. This would be negative 0.8. So matches, right? Because 0 matches is not less than or equal to negative 0.8, it is not significantly low because it must be 0 was supposed to be less than that. Not significantly low. I'm gonna say not significantly low number of matches because 0 matches is not less than or equal than negative 0.8, right? But use the rule of thumb to determine whether 4 matches, where is 4? Yeah, 4 matches is significantly high. Okay, so if you check for 4 matches that is significantly high, okay, let's see, significantly high means mu plus 2 standard deviation. So that means 0.4 plus 2 times 0.6. What the answer would be, if you add it that way, it's gonna be 1.6. Okay, so 1.6 matches because 4 matches is greater than or equal to 1.6. Is greater than or equal, right? 4 matches greater than or equal to 1.6. Is that correct? Matches. It is significantly high, right? It is significantly high. It's significantly, because 4 matches is way greater than 1.6. Okay, so it's significantly high, right? But the other one not significantly low because 0 is not less than negative 0.8, right? So that's why we're gonna do it. Now, probably that would be the next examples here. As you can see, we have a few examples very similar, but I'm gonna do this one and let you do the next probably. Here again, you see we have exactly the same. We know the total is 1 because we did it. Find the probability of getting exactly 2 matches. If you want to get what is exactly 2 matches, yeah, easy to find, 0.292, that's exactly 2. But if you want, for the next one, it says, you know, it says to find exactly 2 matches. So for the next one, it says to find the probability of getting 2 or more. That means probability that X is less, greater or equal to 2. Add everything from 2 to up. So that means 0.049 plus 0.004 plus 0. If you add up all of this, the probability is 0.0 5.3. That would be the answer because it said at least 2. They could say less than 2. Which probability is relevant to for determining whether 2 is significantly high? Remember, that should be more than, greater than, must be less than 5%. So is it less than 5%? Which one is less than 5%? Okay. So the probability from B, part B. All right. The probability from part B, since it's the probability of getting more extreme results, right, is to significantly significantly high number of matches. So look, it's significantly high if you do the mean, even though we don't have it, but we know because 2 standard deviation is not less or equal to 5%. No, it's not, because it's not less than 5%, right? Because it's 5.3%, it's not less than 5%. So it's a no. No, because the probability of 2 or more matches is not low, all right? Less than or equal to 5%. So that's the case. I usually do one and leave one for you because you see this one is exactly the same. Of course, this one, what you can see, exactly one is 0.292. Hey, do I make a mistake in the first one? Because exactly two is definitely not this number. Again, that's is that tiredness? Maybe. Because this is exactly 2 is 0 point. That means we do probability. Let me put it correctly. I said probability of x equal 2 is 0.049. Okay, now here, probability of exactly 1, probability of x equal 1 is 0.292. Probability of x is less or equal to 1 because they said fewer than 1. Remember, we said fewer than 1. That means we take 0.656 plus 0.292. Answer, when we add these two, answer is 0.948. Now, again, which probability is relevant for determining whether 1 is significantly low number of matches, result A or B? Again, if you look at here, you see it's part B, all right? It's part B because the probability of the given or more extreme results, right? Again, that's not true. Here also is one significantly low number of matches. It's a no, because the probability of 0.948 is not low, right? It's not less than 5%. So that's a big no. This probability, 0.948 is not or equal to 0.5. It's not equal to this. So that's why we're gonna do it. I did it because I was leaving it. I was planning on giving it for you, but we did something different, right? Now, let's do a few other examples, and because we have so many exercises to do here. In this one, what we ask you to do again, using the same tables, of course, I said, oh, you know what? These tables, first of all, is it a probability distribution? Yes, it is. Those are X values. So let's say those are X's, and these total probabilities here is, total probabilities is 1. Okay. Now, to find the mean, the access to find, remember, you need to multiply all the X's like you do 0 times 0.066, 1 times 0. You do 1 times 0.238, you do 2 times 0.344, we do 3 times 0.0249, 4 times 0.09, 5 times 0.03. All right, so remember, if sum of x times p of x, again, that's something random, I would say. That's the answer we were doing before, and I thought that, I gave you not the correct one. So that would be our mean. So we know the mean would be 2.1. Again, for the standard deviation, remember the goal of doing standard deviation is to subtract the mean from each of them and multiply it by the p of x. That means we do 0 minus 2.1 squared times 0.66, 1 minus 2.1 squared times 0.238, 2 minus 2.1 squared times 0.344, 3 minus 2.1 squared times 0.249, 4 minus 2.1 squared times 0.09, and 5 minus 2.1 squared times 0.013. So again here, putting the sum x minus the mean squared times p of x, what the answer would be, you need to add up everything. And as I said, you'll find 1.21. And knowing that the standard deviation is the square root of 1.21, so standard deviation would be 1.1. So we find the mean and the standard deviation, okay? So that was the questions we were supposed to answer here for part A, because they said for these 5, find the mean and the standard deviation, which we did, okay? Now, let's answer the next question. The next question says, find the probability of getting exactly 3. So probability that x is equal to 3. What's that probability again? Yes, 0.249. For C, again, C, let me put C here. Probability, the probability of getting 3 or more, that means x should be greater or equal to 3. That means take them all, 0.249, okay? Okay, we do, right? We do 0.249 plus 0.09 plus 0.03. What is this probability again? It's 0.353, 0.352. Okay, that's C. For D, which probability is relevant for determining whether 3 is significantly higher? Again, we go back with these questions. So that's definitely part B. Why? Since it's probability of the given or more result. But again, is to significantly number high? It's a no. Look at the probability, 0.352. It's more than 25.5%. So no, because the probability of 3 or more drivers who say that they text while driving is not low. It's not less than 5%. It's 35.2%. So it's a no. Okay. So knowing this, I'd leave you definitely this one for, because we asked exactly the same question, but with getting exactly 2 or fewer than 2, etc. Now, one more exercise to complete this session is expected values, because for the expected values, the mean of a discrete probability, the mean of a discrete probability variable x is the theoretical mean outcome for infinitely many trials. We can think of that mean as the expected value, in the sense that it is the average value that we would expect to get if the trials come could continue indefinitely. So the expected value of a discrete random variable x is denoted by E. So remember, we call it E, and we said that E is equal to the mean, and E can also be found for us is that you take the sum of x times P of x. Of course, when we said expected value, when you play lottery, let's suppose you buy a ticket for $10 and you make $100 for paying $10. So how much money you really make? Yes, you don't make $100. You make $90 because remember you spent $10 in tickets. So your profit is not $100. Your profit is $90 because you need to remember you invested or you spent at $10 to win that. So that's what the expected values help us to find of a random value equals to the mean. So we can do that this way. So let's do these examples very quick. Probably it's going to be quick, or maybe not. Maybe it's going to be very giantly quick, or maybe it's going to take a long time to get. Let's try it. What we said then, in North Carolina's peak fall lottery game, you can pay $1 to select a 4-digit number from 0 to 000, 4 digits of to 9999. If you select the same sequence of 4 digits, remember you select 4 digits in the lottery that are drawn, you win $5,000. So how many different selections are possible? But remember what you do, you select, okay? Okay. Remember what happened. You are choosing a 4-digit number where each digit went from 0 to 9. So each digit has how many? Each has how many possible? 10. So for us, we know for the first one, you have 10 possible. The second one, 10 possible. The third, because you can repeat them. So taking it that way, it gives you a beautiful 10,000 different possible selections, right? So that's 10,000 because you can choose the first digit from 0 to 9, the second digit from 0 to 9, the third digit from 0 to 9. Even though you take 2, 2, 2, 2, that's not a problem. Even though you want 1, 2, 3, 4, it's not a problem. Even though you take 9, 6, 7, 5, it doesn't matter because you can repeat the digit. What is the probability of winning? Remember, you can only win one, you have only one chance of winning. What is that? Yeah, there are 10 possible outcomes, but there's only one ticket. So 1 out of 10,000, that would be your probability of winning because only one of those 10,000 combinations win the exact one, John. So it's either that way in fractions, or if you want to express this in decimal, put it 4 zeros. Is that 4 zeros, right? Right. No. If you win, what is your profit then? I just told you. Your profit should be, your profit should be like, because you win $5,000, but you spend $1 because you pay the tickets for $1. So you make $4,999, right? So that would be your profit. Okay. Now let's see for D what we can do. D, they said find the expected number. To find the expected numbers, remember, you need to know what is the probability of winning. So expected value, what is the probability of winning? And you multiply it by what you would win. Probability of winning is all depends, Yeah. Probability of you win. And if you win, what you're gonna win? So yes, that would be the profit, net profit if winning. Plus expected value. What is the probability of losing? Probability of losing times net gain, of time lost. Okay, I mean losing of times lost. So for us, probability of winning, we already find it is 1 out of 10,000. If you win, you're gonna make 4,999 plus. Okay, probability of losing, what is that again? Yes, that would be not 4,000. So because it's 9,999, because if you have only one way of it, is 999. Is that 3 9 or 4 nines? 4 nines over 10,000 times the loss. What is the loss? Yes, negative $1. Okay, remember it's $1. So that means when you do this computation like this, answer would be negative 0.50. So for us, what it says, if you play that way, you're gonna lose 50 cents. Okay, so expected values is equal to negative 50 cents. Okay, so you're gonna lose 50 cents. Now, the last question is a little bit subjective. If you bet $1 in North Carolina's pick 3 games, the expected value is which bet is better in the sense of producing a high expected value. A $1 bet in North Carolina pick 4 or a $1 bet in pick 3. Pick 4 and pick 3, it's going to be very close. So it's neither, because both bets have around the same amount. You can do it with 3. We're going to say it's neither. Yeah. All right. So do not hesitate. You can ask me any questions you want. All right. And make sure uh, uh, everything is okay. I'll see you in a different video for another section of this chapter. Take care.